So this is the second class of your new semester. That is, what is this semester? Semester 4, right? So in the previous class, we have started the chapter, a new unit, that is chemical kinetics. So much of introduction, so many topics we have learned in that class, right? Hope you have learned and hope you have practiced once. Okay, so moving on to the next topic, students, from this unit, we have the derivation of rate constant for first order reactions. Okay, so kindly put the side heading first order reactions. Okay, so this can be asked as, the way of asking this question, how can we expect a question from this topic? Derive an expression for the rate constant of first order reactions. Then you are supposed to write the whole answer which I am explaining now. Okay, and also students, this is a very important essay question, most frequently asked question, both in the internals as well as the end semester exams. Okay, so don't worry, I will make I will try my level best to make you understand this answer, and also I will try to make this easy. Okay, right? So when we are asked the question, derive an expression for the rate constant of first order reactions, how to proceed? First and foremost, we are supposed to define the first order reaction. This we have already done in the previous class. But again, here you have to write the definition. Okay, so put the side heading, definition of first order reactions. So how do we define, or what do you know about a first order reaction? A first order reaction is nothing but the reaction in which rate of reaction depends on only one concentration term of the reactants. Okay, so write down the reactions in which rate of reaction depends on the only one concentration term of the reactants are called as first order reactions. Students, you can also write in the other way, that is sum of powers of concentration terms of the reactants in a rate expression is 1. Okay, such reactions we call them as first order reactions. It's your choice. Or simply, if you want to write the reactions for which order equals to 1 are called as first order reactions. Okay, it is completely your choice. Okay, so next, first is the definition mark. Next comes, let us consider a first order reaction. That means the general representation of a first order reaction. See, here I have taken the representation. A gives products. Here the reactant is A. Okay, so write down A. Let us consider a first order reaction. A gives products. Okay, now how to write the rate expression for this reaction? We all know, according to law of mass action, rate of reaction is proportional to concentration of the reactants. Okay, so A gives products is our first order reaction. And the rate expression for this reaction goes like this. dx by dt is proportional to concentration of the reactants. Here what is the reactant? A. Okay. Concentration of A. Written dx by dt proportional to concentration of A. Now next step. If we remove the proportionality, what are we supposed to write? A rate constant. So dx by dt is equal to K into concentration of A. Why did I mark here 1? K1. Because it is the first order reaction. In order to avoid confusion. For second order reactions we use K2. Similarly, third order K3, like that. Okay. So dx by dt is equal to K1 into concentration of A. Mark this as equation number 1. Below you have to write where K1 is called as rate constant for first order reactions. Okay, write down K1 is the rate constant of a first order reaction. Till here anyone can write. Okay. So from here now the problem begins. So try to listen carefully, students. It's not that complicated. So now the reaction is A gives products, students. Okay. So in the beginning, that means the reaction has not started yet. So how then what will be the time? So how to determine time in the beginning? So there will be no time consideration. That means in the beginning, the time t will be 0. Okay, in the beginning, reaction has not yet started, students. Therefore, in the beginning, that means before the reaction has started, the time will be 0. That's what I have written here. Look here, at the beginning of the reaction, when time t is equal to 0, the concentration of A is considered to be. So let us assume the concentration of A in the beginning of the reaction. How much? Small letter A, students, moles per liter. Okay. So which is called as initial concentration. Initially the concentration of the reactant A, let us consider it as A moles per liter. Okay. Moles per liter are the units of concentration. So mention in the brackets initial concentration. Okay. So now the time is passing. The reaction has started. Slowly what happens? A starts converting into products. Okay. So let us think that some 10 minutes are over, 5 minutes over, 15 minutes over. So A will not be A. That means initially how much was there? Small letter A moles per liter was there. But after 10 or 15 minutes, A will not be A moles per liter. Some of it will be converted into products. That means there is a change in the concentration of the reactant. Okay. So what I have written there. So the other part of the board, look here. After some time t, that is within 10 minutes or within 15 minutes, some part of A has been converted into products. So what did I write here, students? After some time t, X moles of initially how many are there? A moles per liter. Small letter A moles per liter are there. But time passed by, so reaction has started. Some portion of this A now converted into products. Okay. So that we are assuming it to be small letter X. Okay. So X moles of A has been changed or converted into products, which we call it as the decomposed concentration. Okay. Suppose there are 100 chocolates on the table. So mama asked you not to touch until she distributed. But you will not listen, right? So slowly you went and after some time you have grabbed some 10 or 20 chocolates. Okay. So that 10 or 20 chocolates will be X, 100 chocolates will be A. Okay. So mom will come and look. So what happened? How many chocolates will be there when you have taken 20 chocolates and put it in your pocket? Only 80 will be there. That is the remaining number of the chocolates. So here also A minus X will be the remaining concentration of A. Now you understood, I guess, right? Because I have taken chocolates, no? Understood? Okay. So initially A moles per liter was the concentration of A mom. After some time what happened? Some portion of A was converted into products. That we have assumed it to be X. This is called as initial concentration and X is called as decomposed concentration. Now if I ask you the remaining concentration of capital A, how much? A minus X. Okay, so this is initial concentration, X is the decomposed concentration, A minus X is the remaining concentration after time t. Initially time t is 0. Initially concentration was small letter A moles per liter. Within some time X moles of A has been converted into products, which is called as decomposed concentration. So finally, after the reaction has completed, that is after time t, the remaining concentration of A was observed to be A minus X moles per liter. So we have learned initial concentration, decomposed concentration and remaining concentration. Okay. So now what to do with this remaining concentration? So let us proceed with the derivation. Okay. So students, substituting the remaining concentration of A in equation 1. Okay. So what is your equation 1? dx by dt is equal to K1 into concentration of A. The remaining concentration of A, how much? A minus X moles per liter. So substituting concentration of A, that is A minus X moles per liter in equation 1, we get dx by dt is equal to K1 into A minus X. Okay, write down. dx by dt is equal to K1 into A minus X. So this will be your equation number 2. Next, look here, what did I do? dx by A minus X. So bringing the same variables to the same side, dx by A minus X. So this A minus X, I brought it here students, is equal to K1 into, now this dt will come to the right side. Okay. So dx by A minus X is equal to K1 into dt. Till here understood, I did not do anything. Just substituted the value of A here. Next, A minus X, I brought it here. So dt, now it will come this side. Now, integrating this equation on both the sides. Okay. So, if you have space here, you can write here or else write here in the brackets. Integrating the above equation on both the sides. Okay. Fine. So, how to do the integration, students? So, you know differentiation and integration. So, integral symbol is this one. So, integral dx by A minus X is equal to K1. K1 cannot be integrated because it is a constant. K1 into integral dt. So, what did we do, ma? So, we are integrating this equation both the sides. So, how do we write? Integral dx by A minus X is equal to K1 into integral dt. Sorry, mark this equation as 3. Mark this equation as 3. Okay. Now, so till here I think it is easy. Below this step, okay, write down, put a star mark and write down. We know that. So, we are using solution of this integral dx by A minus X. So, we don't derive again separately. We directly take the solution of that and use in our equation. Okay. So, that's why you have to remember wherever you are putting the star marks. We know that is from mathematics. We know that integral dx by A minus X value is minus logarithm of A minus X minus logarithm of A minus X plus constant. Okay. So, here we are using two constants. That's why to mark a difference between these two, I have used C1. But generally, it is a constant. Okay, students, put a star mark, write down. We know that integral dx by A minus X value is minus log of A minus X plus constant. Suppose here there is dx by x, students, minus log x plus constant. Okay. So, whatever is there in the denominator. So, integral dx by A minus X value minus logarithm of A minus X plus C1. And we also know the value of integral dt, which is equal to t plus constant. Okay. So, we are taking two constants. Therefore, write it down as C1 and C2. Students, integral dx value x plus constant. Integral dy constant. Integral dy value y plus constant. So, integral dt is equal to t plus constant. In the brackets mention where C1 and C2 are constants. Put it in a box. You should remember these values. Okay. Now, we will use these values in equation 3. Have you written, students? This is equation 3, not equation 2. Sorry. This is equation 3. Okay. Now, substituting these values in equation 3, what do we get? Integral dx by a minus x value, we have it as minus log a minus x plus c1 is equal to k1. See, k1, don't forget k1. k1. Integral dt value, we have it as t plus c2. So, k1 into t plus c2. Right? Now, is equal to, open the brackets, k1 into t, k1t plus k1 into c2, k1 c2. Okay? Is equal to k1 into t plus c3. Why c3 I have taken? c3 is a new constant. k1 is a constant. c2 is a constant. So, constant into constant, a new constant. Okay, students? k1 into t plus c3. Now, what you do is, I am giving 1 second time. Bring this c1 to right side. So, what will be the next step? Start writing. Minus log a minus x is equal to k1t plus c3 minus c1. Okay? If c1 comes to the right side. So now the next step, minus log a minus x is equal to k1t plus c. c3 minus c1, again I am taking it as a new constant because both are constants. c3 minus c1 is a new constant. Write it down as c, students. Okay. So what did we do? c1, we moved it to the right side. Next, c3 minus c1, we are writing it as c. Okay. That will be equation number 4. Mark it as equation number 4. Okay, students. Now, below write down, when time t is 0, when time t is 0, obviously decomposed concentration, that is x will be 0. Okay. So that only write down, when time t is 0, x also will be 0. When time t is 0, x will be 0. Now, substituting these values in equation 4. Substituting these values in equation 4. Can you write it down on your own without looking at the board? Yes. Minus log a minus x value is 0. So, a minus 0 is equal to k1 into 0 plus c. k1 into 0 becomes 0. Therefore, c value will be minus log a. Okay? Minus log a. Now, what shall we do? We will substitute the value of c in equation 4. Write it down, students. Here I have not written. Please write it down in your notebooks. Substituting the value of c in equation 4, we get, what is that? Minus log a minus x is equal to k1 into t. Now, in the place of plus c, we have to write minus log a. That's what I have written here. So, minus log a minus x is equal to k1 into t minus log a. Okay. Now, below. So, minus log a. We shall bring this to left side. It becomes plus. So, when it comes to left side, log a minus log of a minus x, log of a minus x is equal to k1 into t. Okay. So, just bringing minus log a to left side. Now, here again, star mark. What is the meaning of star mark? You have to remember that. So, we know that log m minus log n is equal to how much? Log m by n. So, applying this to our equation, log a minus x. If this is m, if this is n, then it becomes log a by a minus x. Very good. So, next step, log a by a minus x. is equal to K1 into T, K1 into T. Equation number 5. Equation number 5. Below, star mark. Log of, we know that log of x base e. There will be two types of logarithms, base e logarithm and base 10 logarithm. So base e can be converted into base 10. How? So here I have given one example. Look here. Log of x base e is equal to, if we multiply with 2.303, then we can convert into base 10. So we know that, here you write down, even if you don't know, write down. We know that because these are all we have learned in the mathematics in your earlier classes. So log of x base e is equal to 2.303 into log of x base 10. Written? Okay. Now we will apply this to our equation. So log of a by a minus x base e. Here I have written log of a by a minus x base e is equal to 2.303 into log of a by a minus x base 10. Okay. So base e can be converted into base 10 by multiplying with 2.303. Okay students. So log of a by a minus x base e. So I did not write here, means it is in the form of base e. We are converting into base 10 so that it will be easy for the solutions. So how did we convert? By multiplying with 2.303. Now what you are supposed to do, write down this next step. So this equation is there now. So write down next step. 2.303 log of a by a minus x base 10 is equal to K1 into T. Will you be able to write? So write down. So students, 2.303 log of a by a minus x base 10 is equal to K1 into T. So from this equation, we can write for K1 is equal to, write down students, K1 is equal to 2.303 by 2. That means T is with K1. So T will go to the denominator. So 2.303 by T remaining same. Log of a by a minus x base 10. Okay. So go back and check what the way of asking the question of this answer. So what did I tell you in the beginning? Derive an expression for the rate constant of first order reactions. So we have done it. K1 is equal to, what is K1? Rate constant of a first order reaction. So the expression for rate constant of a first order reaction is 2.303 by T log of a by a minus x base 10. Put it in a box. Okay. Below write down units. Units of K1. So how will you find out the units for K1? So K1 expression 2.303 by T. T is what? Time in the denominator. Next A by A minus X. What is A? Initial concentration. Units of concentration moles per liter. A minus X is also concentration moles per liter. So both gets cancelled. So what is remaining in the denominator? Time. So if it comes up, time inverse. Okay. So when you should be careful. It depends upon the time given in the numerical. Seconds or minutes or hours, like that. Okay. So if it is seconds, then you should be able to write seconds inverse, minutes inverse, like that. So units of K1 are time inverse. Okay. So not yet completed, students. Below put the side heading. Characteristics of first order reactions. Characteristics of first order reactions. Number one. K1 values obtained at different concentrations. K1 values obtained at different concentrations are always constant. Okay. So generally, you will be having practicals based on this in final year, students. So you should remember this unit even after going to your final year. Okay. So, with at any concentration, like if you are calculating the K1 value for various concentrations, it remains constant. Okay. Then only our experiment is correct. If we are not getting the constant value, then there is an error in our experiment. Okay. K1 values obtained at different concentrations are always constant. Next, second point, K1 values doesn't depend upon the units of concentration. So here you have seen units of K1, time inverse. So K1 values are not depending upon the units of concentration. Next, third point is a very, very important point which will be often asked as a short answer question. So what is the third characteristic? Half-life is independent of initial concentration. So what is meant by half-life? The time taken for the decomposition of half the initial concentration of the reactants is called as half-life. Okay, what is half-life, students? The time taken for the decomposition of half the initial concentration of the reactants is called as half-life. So, how to show this? That this half-life is not depending on initial concentrations. So, we shall do that. First write down, we know that K1 is equal to 2.303 by T log of A by A minus X base 10. So, kindly write down the equation for K1 and below write down when T is equal to T by 2, that is half the time, which we write it down as T half. When T is equal to T half. So, generally half-life we represent like this, T half or T by 2, that means T half. So, when T is equal to T half, then X will be equal to A by 2. A by A is initial concentration, half the initial concentration. So, the decomposed concentration is half the initial concentration. So, when T is equal to T half, X will be equal to A by 2. Now, what you do? Substitute these values in this expression. Okay? So, after substituting the values, we get K1 is equal to 2.303 by T half. In the place of T, we are writing T half log of A by A minus A by 2. X value we are substituting as A by 2 base 10. Okay, shall I read it once again, students? K1 is equal to 2.303 by T half log of A by A minus A by 2 base 10. So, next step will be 2.303 by T half log of A minus A by 2 is A by 2. 1 minus half na. So, A by 2, here write down base 10. Okay. So, A by 2 is how much? A gets cancelled, 2 goes up. So, 2.303 by T half log of 2 base 10. So, logarithm of 2 value 0.3010. So, 2.303 into 0.3010, if we multiply, we get 0.693 by T half. Okay. So, left side we have K1. Therefore, T half is equal to 0.693 by K1. Okay. Half-life is independent of initial concentration. In this expression, you are not finding any initial concentration. Okay. So, we have proved it now. The third characteristic. Okay. So, now write down examples. Examples you can write down inversion of cane sugar and acidic hydrolysis of an ester. Go back, in the last class I have given these two reactions. Don't simply leave empty here. Examples, those two you write down. What are the two reactions? Inversion of cane sugar, write down the reaction. And second one, acidic hydrolysis of an ester. So when you are asked this question, till here you are supposed to write your answer. Okay. Definition of first order reactions, representation of the first order reaction, then rate expression, then integration, then the complete derivation. After deriving the expression, we have to write the characteristics. And in the characteristics, the third point is very, very important. If this first order derivation is not asked, then half-life will be asked. Okay, so show that half-life of first order reaction is independent of the initial concentration. Then you are supposed to write the third point, and at the end you have to write the examples. Okay, so suppose if I am correcting your papers, if there are no examples, I will simply cut half mark of your answer. So draw a line till here, students. This is the entire answer for your, what is that expression for rate constant of a first order reaction. So now comes the most interesting part, that is numericals. Do you like it? Okay, so even if you like or not, we have to do the numericals, and also we have to practice them, because whenever the question is asked, there will be an attached numerical with it. At least it will have 2 marks minimum. Okay, so write down the problem number 1. The half-life period of a first order reaction is, the half-life period of a first order reaction is 2 hours. 2 hours. Okay, so time is given in hours, students. Full stop. Calculate the time taken. Calculate the time taken for the completion of 87.5% of the reaction. 87.5% of the reaction. Students, the solution for this can be divided into 2 portions or 2 parts. So first sentence, half-life for the first order reaction is given 2 hours. Okay, from this we can calculate rate constant, that is from the third characteristic. Okay, T half is equal to 0.693 by K1. So from this we can calculate K1, and the second portion we can use the K1 value and determine or calculate the time taken for 87.5% completion of the reaction. So how to do this? Put the side heading solution part A or part 1. Part 1. Write up. K1 is equal to 0.693 by T half. 0.693 by T half, which is equal to 0.693 by 2. T half is given as 2 hours. So 0.693 by 2, when we divide, we get the answer as 0.3465. Don't forget to write the units, students. That is hours inverse, because the units of K1, time inverse. Here the time is mentioned in hours. So 0.3465 hours inverse. Next, part 2. So we will use this K1 value obtained in part 1. Write down. K1 is equal to 0.3465 hours inverse. Next, A, that is initial concentration, let us assume it to be 100. It is not given in the problem, students. It is just given how much percentage is completed. That is the decomposed concentration, which we use the letter X for it. Okay, so if we take A as 100, X is how much? 87.5. So A is 100, X is 87.5. So from these 2 values we can determine A minus X. That is too easy. A minus X is 12.5 moles per liter. Now calculate the time. Second part, T is equal to question mark. So I have given everything. So take the formula. K1 is equal to 2.303 by T log of A by A minus X base 10. Substitute all the values. Okay. So T is to be calculated, students. Therefore, I have written one more step again. I need not write it. But T is equal to 2.303 by K1. K1 comes here. Log of A by A minus X base 10. So is equal to 2.303 by K1 value is 0.3465 into log of 100 by 12.5. A minus x 12.5 base 10. So is equal to 2.303 by 0.3465. 100 by 12.5 is 8. So logarithm of 8. Okay. So log 8 value is 0.9031. So if we divide 2.303 by 0.3465, we get 6.646 and so on. You can stop here. So is equal to, if you multiply 6.002 hours, even if you write 6 hours, it will be correct. Okay. So this is the way we solve this kind of problem, students. And I am giving a small homework. So problem number 2, I will just give the problem. You have to solve it. Okay. So write down a first order reaction. A first order problem number 2, students. Don't move here and there. Just within few minutes we will complete the class. A first order reaction is found to be 15% completed in 20 minutes. Is found to be 15% completed in 20 minutes. Full stop. Calculate the time taken to complete 75% of the reaction. A first order reaction is found to be 15% completed in 20 minutes. So here A is 100, X is 15, T is 20 minutes. Okay. So you can calculate rate constant using these values. Next point, next portion or next part. Calculate the time taken to complete 75% of the reaction. Okay. So 75% of the reaction, X is 75, A is 100, K1 value, the one which you calculate for the first portion, you can calculate and determine, you can use and determine the time. Okay. So this is the homework for you. Please try to solve it. So I need not give the same problem in your exam. I might change or I might use my own ways of giving a numerical. So try to do the second numerical. So this is all for this class, students. Hope you have enjoyed it. Please don't throw the book aside immediately after the class. You in the evening or sometime like that, after relaxing, you please practice it, or else by the time we learn second order reaction, we will not remember anything. Okay. So practice well, read well, and take care, students. We will meet in the next class. Bye bye.